Now on to stoichiometry. So this video will refresh you on the classic stoichiometry problem that we often call mass, but we don't have to know that. We just have to know how to perform a stoichiometry problem. But of course, stoichiometry problems could come our way and involve limiting reactants. They could also ask for or involve percent yield. All right, the very first thing is we need to make sure that we can balance a chemical equation and interpret it. We need to know that reactants are on the left side of the arrow, which literally means yields. Reactants yield product or products. We have phase symbols that convey the state of matter, or possibly that it's an aqueous solution dissolved in water. Why do we balance with coefficients? That's of course to respect the law of conservation of mass. Here are some examples with the answers. If you want to pause and go ahead and do those, but that's for extra practice. So we're going to start this definitely with the understanding that you, with 100% accuracy, can balance a chemical equation and understand the different information that could be conveyed to you through phase symbols or the side of the reaction arrow that your substances are on. All right, so digging in. I'd like to first off make sure we are clear on exactly what these coefficients can be interpreted to mean. They could be at the atomic and molecular level, meaning that this means 4 hydrochloric acid molecules, covalent, so molecule, reacts with 1 formula unit, because this is ionic, so the smallest piece we call formula unit, to make 2 water molecules, 1 manganese 2 chloride formula unit, and 1 chlorine molecule. However, we're normally not on the level of working with individual molecules or formula units, so we know these mean moles. So I can interpret the coefficients to be moles, and that's how I get mole ratios. So I can trust that if I have a balanced equation, and that is the first place we start, we have to have a balanced equation before we can do stoichiometry, because that is how we relate one substance to any other substance within the reaction. So for every 4 moles of HCl, I will have 1 mole of MnO2, but I could also say, well, for every 4 moles of HCl, I'm going to make 1 mole of Cl2, and so on. So you can relate reactant to reactant, reactant to product, product to product, product to reactant, anything to each other, as long as you have the balanced formula, which become mole ratios. There will be a 1 mole ratio in every stoichiometry problem. So if we could dig in just to remind you of the basics. So we're given information about an ore of iron, so a compound or a substance, that part of it is how we can obtain pure iron. So we get some pure iron by reacting this ore with carbon monoxide, and then we're getting the pure iron and then carbon dioxide. And notice we're already given the balanced equation. Now, I'm going to rewrite that, not that you have to. Now, I'm acknowledging, of course, that I'm given phase symbols, but I'm just going to not rewrite them just to keep it a little clutter-free. I may need them though. All right. So I'm asked how many grams of iron can be produced from the reaction of 1 kilogram of this hematite. I like to, you are not required, but I like to write what I am given underneath that species and then what I'm trying to look for. Now notice we are given a mass unit and then we're asked for a mass unit. So that's why these types of problems are often called mass problems, but we don't have to know that. Okay, so we have our balanced equation. Let's dig in. We're going to start, of course, with our given. All right. Now, I know that every problem in stoichiometry will involve a mole ratio. How do I know it's stoich? Because I'm given one thing in a reaction and asked for another thing in the reaction. So I know I'm going to translate myself from the given to what I'm trying to find in terms of moles. So whatever we're given, our focus should be to get to moles. Well, I mean, I could go from kilogram to moles, but why don't we go to grams? Usually this is where students make a misstep, so I'm going to go ahead and just show that. Plus the College Board often loves to see correct metric unit conversions. All right, now I know that once I have grams, I can go to moles. And you would calculate the formula mass, 2 irons and 3 oxygens. That will be 159.70. Make sure you're reporting minimally to the 100th place. Now that is the formula mass in 1 mole. I would always put formula masses per 1 mole. So even though in a moment we're going to go to iron, which has a coefficient of 2, if I need the mass, if I get the value right from the periodic table, we know that is per 1 mole. I would reserve using coefficients for the mole ratio only. All right, so I've gotten myself into moles of my given. Now I can do my mole ratio. For every 1 mole of Fe2O3, I will make 2 moles of iron, and I know I can go right to grams. And there again, if I'm going to use my number from the periodic table, 55.85, that's in every 1 mole. Now, if you want to put a 2 there, that's fine, but then you have to double that. Remember, these have to be true relationships. But whenever we're going from moles to grams or grams to moles, why don't we just interpret the formula? All right, and I've accomplished what I needed. I will have my grams of iron and 3 sig figs. This would be 5. These don't limit, these don't limit. This, of course, is exact, and there's 4, so I'm limited to 3, and my answer rounds to 699 grams of iron. Okay. All right. Limiting reactant. So, how do we know it's a limiting reactant problem? Well, if we take a look, and I like to rewrite my equation. You do not have to. All right, and let me just make sure. Oh, yep, I'm already given it as a balance equation. If you're not given a balance equation, it often will say, like, according to the unbalanced equation. But it's good for us as chemists to definitely check and make sure. All right, what mass of hydrogen peroxide should result when 1.50 grams of barium peroxide is treated with 25 milliliters of a hydrochloric acid? Oh, it's a solution. So I have HCl dissolved in water. So it's 25 milliliters of the solution. That is not all HCl. There's some water in there. 25 mils of a hydrochloric acid solution, and the solution contains 0.0272 grams of HCl per milliliter of the solution. So for every 1 milliliter, and because this is 3 sig figs, I'm going to put 1. Oh, so that actually could maybe be a conversion factor. All right. And then what mass of each reactant is left unreacted? All right. Ooh, I got a little crowded. So I'm after the mass of this, and I have this given and these givens. And if I take a look, I am given things about both reactants. Dun, dun, dun. So that is how we know it's a limiting reactant problem. Usually, the amount of product is dictated by one of our reactants. One of the reactants will be used up first. And once you run out of reactant, you stop producing product. That's what makes the limiting reactant limiting. It limits the amount of product because it runs out first. Okay, so we need to find out, well, how much of this are we going to get? And do you know, whenever we find that, it will answer for us what the limiting reactant is. So oftentimes, a limiting reactant problem will not have limiting reactant in any of the wording. We have to know how to diagnose that. And that again, if you have at least two givens and the givens are both reactant quantities. Now you could have more than two reactants, but still, if you are given amounts of two, it will be a limiting reactant problem. There are different ways that you can actually find your limiting reactant. And usually the way that we approach a limiting reactant problem is based upon how we were taught. And depending upon who you had for honors chemistry, you may have been shown a little bit of a different method. I'm going to prioritize the method that will answer the majority of questions that were asked in AP chemistry. So, what I'm going to do is go ahead and start with the amount of each reactant and do a Stoich problem one reactant at a time. So I'm going to start with 1.50 grams of barium peroxide and ask, okay, how much hydrogen peroxide will that amount give me? Pretending I have all the HCl that I need. But then I'm going to do the same for the amount of HCl to determine how much hydrogen peroxide I'm going to get, pretending that I have all the barium peroxide that I need. So that will tell me how much product this will give me, how much product this will give me, and then I go from there. Okay, so quickly setting up. Now I'm given mass of this first starting reactant, and so it's just a mass problem. Don't worry that this is talking about an aqueous solution here, because ultimately what we'll just find out is the mass of H2O2, the actual product. So, yeah, it's in aqueous solution, but what our answer will be is the mass of H2O2 that's within that aqueous solution. So we are fine to just go from mass of this to mass of that. So this is formula mass 169.33 in 1 mole. And then I know once I get moles, I can do my mole ratio. So for every 1 mole of barium peroxide, it is 1 mole of H2O2. And for every 1 mole of H2O2, because I'm asked for grams, I'm going to go ahead and go to grams, even though finding moles of this would also answer the limiting reactant. 34.02 grams of H2O2. And I get 0.301 grams of H2O2 from that amount of barium peroxide. Okay, now what about the HCl? I have volume of solution and a ratio of grams of HCl per volume of solution. I have 2 givens. You really could start with either, but I highly suggest starting with your simpler given, starting with the non-conversion factor. So, I have 25 milliliters of my HCl solution. Well, I know my first step. I don't want milliliters of solution as my final answer. So I know my first step will be to cancel milliliters of HCl solution. And I know ultimately I want moles of HCl. Well, this is where we can use this. For every 1 milliliter of that HCl solution, there's 0.0272 grams of HCl. Oh, and then if I know grams of HCl, I can get moles. Oh, and then once I have moles, I can do my mole ratio. Okay, don't stop yourself. Think through the problem. You definitely have the brains to be able to work these problems. All right, so once I get to grams of H2O2, and this will be 0.317. Okay, so what gives me my smaller quantity? The barium peroxide. This is my limiting reactant. A limiting reactant has to be the reactant. So I wouldn't say this is limiting. This is what gets limited. I'm not asked for the limiting reactant in the problem, but if I were, that's it. what do I call the other reactant an excess reactant? Because some of it will be left over. So, to answer the question, first, how many grams of H2O2 will I get? And it would be that answer, 0.301. Now, it's not that this is wasted. I needed to find this because this allows me to compare to know that this is the correct answer. But I'm not going to get this amount of H2O2, right? This limits me, so this will never be actualized. Okay. The next question asks, what mass of each reactant is left unreacted? Well, what makes the barium peroxide limiting is the reaction stops when it runs out. So, after the reaction, there are 0 grams of barium peroxide that remain. Okay, we can take that to the bank. We know that. Okay, then what do we do to find how much of the hydrogen peroxide remains? I'm sorry, of the hydrochloric acid remains. All right, my suggestion, whatever is limiting is in control. This barium peroxide determines the amount of H2O2 that's made, the amount of barium chloride that's made, but also the amount of HCl that reacts. So what I would do is a Stoich problem to answer, okay, I know all of this BaO2 will react. Well, how much HCl will end up reacting with that? And so, grams of BaO2 in 1 mole of BaO2, and then for every 1 mole of BaO2, I will react 2 moles of HCl, and every 1 mole of HCl is 36.46 grams. Okay, so that's what Stoich tells us, is how much will react, how much will be produced. And so 0.646 grams of HCl actually react. Well, how much am I putting in? Well, you have a 25 ml HCl solution, and that solution for every 1 milliliter is 0.0272 grams. And so I am putting in 0.680 grams. And so to get the amount that remains, I take what I put in, 0.680, subtract what the Stoich tells me I will react, and I have how much remains, 0.034 grams of HCl remain. Okay, so often we are just asked, okay, how much of a certain product? Well, then we would stop there. If we were asked, what is the limiting reactant? Well, we have to do this work, and then we can answer. What is the excess reactant? Well, we have to do this work, and then we answer. But what also is valuable is to know, okay, what exactly remains in your beaker at the end? So we understand in our beaker that we will have produced this amount of hydrogen peroxide. We will have produced some barium chloride. We didn't have to find that, but we know we're making that as well. And we're going to have some HCl left over, but not any barium peroxide, because that is our limiting reactant. Okay, so a nice refresher, ladies and gentlemen, on some basic stoichiometry.